Hey guys, this is Mrs. Harbin, and today we are starting Pre-Calculus Unit 5, which is all about different types of equations. And we are going to start with polynomial equations. Now, polynomial equations are not new to you. You were introduced to them in Algebra 2, so hopefully this is a little bit of a refresher. You may see some more difficult problems than you saw in Algebra 2, but the theorems and the steps are exactly the same. If you've forgotten everything you did in Algebra 2, hopefully as we go through these examples, you'll be reminded of those things that you've already learned. Our biblical correlation for this unit comes from Ephesians 10 through 18, which talks about the armor of God. And it says, "Finally be strong in the Lord and in his mighty power. Put on the full armor of God so that you can take your stand against the devil's schemes." Now you may be wondering what that has to do with math. Well, we're told that the armor of God is made of all these individual pieces and that together may make us strong in our faith and strong against the attacks of the devil. When we're talking about math, you're learning all of these different components and pieces, and we know that together we can use these skills to solve more advanced or challenging problems. And we need to be able to solve problems so that we can take care of the world around us in whatever career or shape or form that looks like. Math is a way that we can make sense of the world around us and help take care of God's creation. And so it's really important that we learn these individual pieces or parts, just like the armor of God is important in its individual pieces or parts as well. Our lesson objective for today is that you, the student, will apply factor and rational root theorems to find roots of polynomial equations, and solve polynomial equations. Now, the factor theorem and the rational root theorem, again, were introduced in Algebra 2. But if you've forgotten what you've learned since then, that's okay. We're going to go through some examples and refresh your memory. So as a reminder, a polynomial equation is solved by first setting the polynomial equal to 0 and then factoring the polynomial. We've got different kinds of polynomial equations. We've got first degree polynomials, which look like this. Y equals x or y equals 3x. Those are first degree polynomial equations, and we know how to solve for x if we were trying to find the value of x. Quadratic equations are second degree polynomials. So that's y equals something like this, 3x squared plus x minus 7. And we know that we solve quadratics or second degree equations by taking square roots, by factoring, or by using the quadratic formula. Negative b plus or minus square root of b squared minus 4ac all over 2a. Don't forget about that. So those are second degree polynomials. So those are the ways that we would factor that. The way that we solve higher degree polynomials, however, is a little bit different. And that's what we're going to look for today. One of the theorems that we need to know when dealing with any polynomial is this factor theorem. And here's the definition. If p of r equals 0, where r is a real number, then x minus r is a factor of p of x. And sometimes definitions can be a little bit lengthy here. But basically what this says, if we plug in a real number into a function and we evaluate it and we get 0, that tells us that that number that we plugged in is a factor or a 0 or a root. Remember, there are all these different words here, a root of that function. And zeros and roots and factors are all referring to where our polynomial crosses the x-axis. So let's say we plug in 2 to our polynomial, and we get 0 when we plug in 2. What that tells us is that at some point our graph either crosses or touches at x equals 2. 2 is a 0 or a root, and x minus 2 is the factor. Now, it might make more sense when we start plugging in some numbers here. As a quick reminder, a polynomial equation of degree n has exactly n roots. The sum may repeat or be complex. So x to the first power has exactly 1 root. That's a linear equation, and you should know that it crosses the x-axis 1 time. X squared, degree 2, has exactly 2 roots. Those sum may repeat or be complex, and if you know or remember, x squared is the shape of a parabola, and that can cross the x-axis at most 2 times. So x cubed would have 3 roots, x to the 4th would have 4 roots, etc. The remainder theorem can be used to check for zeros. So let's talk about how to use the factor theorem and the remainder theorem. So we're going to use synthetic division to determine whether -2 is a root also called a 0, of the equation 3x cubed minus 8x squared plus 5x minus 2. So we're going to set up our synthetic division problem, -2, and then we're going to use our coefficients, making sure that we have all of our terms in descending order. Cubed, squared, linear, and then a constant. So let's write those down. 3, -8, 5, and -2. If you've forgotten how to do synthetic division, don't forget you bring down the first term, and then you multiply by what's in this little box here by that first term. So -2 times 3, and your answer goes right there. -2 times 3 is -6. We add these together. -8 and -6 is -14. And then repeat the process. Multiply 28, add 33, and then multiply again, -66, and add -68. So we have determined, because there is a remainder, that -2 is not a root of this equation. What the factor theorem says, essentially, is that we could also just plug -2 in. We could take 3 times -2 cubed minus 8 times -2 squared plus 5 times -2 minus 2. And if we did all the math, we would also get -68. So the factor theorem says that if you plug in a number and you get 0, then it's a factor. If you divide and you get 0, it's a factor. These two theorems kind of go hand in hand, right? And the remainder theorem says you can either divide to find the remainder, or you can plug it in. If I were to plug in this number, my remainder would be -68. So there's really two different ways that you can evaluate these polynomials. Synthetic division is probably going to be the quickest way. But when we divided by -2, we had a remainder of -68. So -2 is not a root. All right, so let's try synthetic division to determine whether 2 is a root. Now we could plug in chug and see if we get 0, or we could use synthetic division. I think synthetic division is a little bit faster. So when we divide by 2, bring down the 3, multiply and add, multiply and add, multiply and add, and we do get a remainder of 0. So x minus 2 is one of our factors. Since 2 is a root, x minus 2 is a factor. And then this becomes our depressed polynomial. Okay, this is always your remainder, so we kind of skip over that last number, and our depressed polynomial then goes this way. This is our constant. This is our linear term, -2x, and this is our quadratic term, +3x squared. So that's how we would write both the factor and the depressed polynomial. So 2 is a root, x minus 2 then is the factor. Since p of 2 equals 0, the factor theorem guarantees that x minus 2 is a factor of the polynomial. If we had evaluated that polynomial by plugging in 2, we would have found the answer to be 0, 0 equals 0. So the factor theorem guarantees that x minus 2 is a factor of the polynomial since 2 is a 0. So x equals 2 is a solution of 3x cubed minus 8x squared plus 5x minus 2. It's not the only solution, because there is an x cubed term here. We know that we have at most those 3 solutions. So we would have to work with our depressed polynomial to find our other solutions. But now it's a quadratic, so we could solve our quadratic by taking roots, factoring, or using the quadratic formula. Let's solve x cubed plus 4x squared minus 2x minus 8 equals 0, given that x plus 4 is a factor of the polynomial. So we're going to start with synthetic division. Since x plus 4 is the factor, x equals -4, We'll then write our coefficients of the cubed, squared, linear, and constant terms, and begin our process of synthetic division. Bring down, multiply, bring down, so add 4 minus 4 is 0, and multiply -4 times 0, which is 0. Then we add -2 and 0, -2. And then we multiply -4 and -2 is +8, and -8 plus 8 is 0. When you are doing synthetic division, be very careful of your negative signs and positive signs. It's very easy to drop those negatives or to forget to write it, and it's going to change your whole answer. So be very careful, be very cautious regarding those negative signs that you don't drop them. All right, so we know that x plus 4 is one of our factors, and now we have our depressed polynomial. This is the remainder. We don't write that. This becomes our constant term. This becomes our linear term. This becomes our squared term, and if we had more, we would continue x cubed, x to the 4th, so forth and so on. So we're left with x plus 4 and x squared minus 2 as our two factors. What we're going to do, because of the zero product property then, is set each of those factors equal to 0. So x plus 4 equals 0, and x squared minus 2 equals 0. Here we can just subtract the 4 and get x equals negative 4. But here, when we add 2 to both sides, we get x squared equals positive 2. We then have to take the square root of both sides, and we get x equals plus or minus square root of 2. Going back to our original polynomial, this was an x cubed polynomial, so we know that it has 3 roots. And you can see we have 1 and then 2, 3 over here. The only possible rational roots of a polynomial equation, and this is just the mathematical kind of notation or definition, if you will, for a polynomial equation. So the only possible rational roots of a polynomial equation are of the form CD, where C is a factor of the constant term and D is a factor of the leading coefficient. So we've looked at the factor theorem, we've looked at the remainder theorem. Let's talk about the rational root theorem. So we have x to the 4th plus 3x cubed minus 21x squared minus 9x plus 54. And before we were starting with synthetic division, but we were being given numbers to divide by. When you're not being given numbers to divide by, it's kind of like being given a whole keychain, a whole set of keys. And you know that one of them opens the door. You just have to go through each one and find it. So what this does, this rational root theorem, is going to create a set of possible keys for us, a set of possible zeros. We're then going to have to try one by one until we find one that works so that we can get a reduced polynomial and do something else like factoring or using the quadratic formula. So to get our whole set of keys, all of our possible roots, we're going to take all the factors of our constant term, which is 54. And the factors of the constant term are 1, 2, 3, 6, 9, 18, 27, and 54. Notice that we have plus or minus because we could take negative 1 times negative 54. So we need to include both the plus and the minus. Our leading coefficient is 1, and our factors of 1 are just plus or minus 1. And then we're going to write all of our possible roots. 1 over 1, 2 over 1, 3 over 1, 6 over 1, 9 over 1, 18 over 1, 27 over 1, 54 over 1. So we now have our whole set of keys here. We're now going to start by testing our keys until we find one that gives us a 0. And I typically start with a positive 1. It makes sense just to start from the beginning. So let's go ahead and we're going to skip past 1 and negative 1 here because I'm going to tell you they don't work. If you try 1, negative 1, it wouldn't work. So let's go into 3 instead. Right. So we're going to divide by 3, and we've got our leading coefficients of 1, 3, negative 21, negative 9, and 54. Remember that if we are missing a term, like if there were no x squared term, we would have to put a 0 there as that placeholder. So following the process of synthetic division, I'm going to go through this really quickly here. We find out that we have a 0. That is our remainder, so now we're going to write our depressed polynomial. This is our constant term, this is our x term, this is our x squared term, and this is our x cubed term. So we're left with the fact that we still can't factor just yet or use the quadratic formula because we still don't have an x squared term. So what do? Well, we try another key, if you will. We try another possible rational root. And just for the sake of this example, I'm going to tell you to try negative 6. Again, using synthetic division, we get down to 0 remainder. So we have 2 roots so far, and we now have a reduced polynomial that we can actually factor. So we've got x minus 3 times x plus 6 times x squared minus 3. When we set each of those equal to 0, we get x equals 3, negative 6, and plus or minus 3. So 4 roots, just like we said we should. All right, I'm running out of time, so I'm going to leave you to solve this one on your own. You can check your work on page 225 of your books. And I'll go through the screen really quickly here. You can pause if you need to,